All right, now I think I'm finally ready to start with what we're going to talk about today. So, all right, so to this point, we have been talking about junctions as kind of an abstract thing. Today, we are going to start talking about PN junctions in circuits, which are much more commonly called diodes. So to this point, we've really only discussed one model called the Shockley model or the exponential model of a diode. So let's start diode models. Okay. So let's start by defining something that you should be familiar with. The circuit schematic symbol for a diode. The side with the triangle is called the anode, and the sign with the bar is called the cathode. For a diode, our voltage drop will always have this particular polarity. So the positive polarity terminal is the anode, and the negative polarity terminal is the cathode. So the way that I like to remember that is the negative polarity terminal goes with the big bar, or a minus sign tacked on the end of that arrow there. So that's how I remember that. And positive current flow is in this direction, from anode to cathode, or in the same direction as the big arrow. So it's pretty easy to remember how things are supposed to behave in a diode. So to this point, we have talked about, as I said earlier, the Shockley model, which says that our diode current ID is equal to our reverse bias saturation current IS multiplied by EXP of VD over, VT. Minus 1, where VT is our thermal voltage equal to kVT over Q. So this equation is the exact same thing that we derived and dealt with on Wednesday, except that we've multiplied our current densities by the cross-sectional area to give us a total current instead of the current density itself. This is exactly what we've spent the last few days deriving how these guys behave. Now we can see inherently that this is a non-linear equation, meaning that the voltage and current aren't proportional to each other, nor are they proportional to the derivative or proportional to the integral, right? We have an exponentially varying function here, so we have non-linearity, and at times that can make how we approach circuit analysis using diodes very, very difficult. So we're going to start with a pretty simple example where we can actually use the Shockley model to determine what's going on. So let's say that I have the following circuit. I have a 2 milliamp source, an unknown resistor, R1, connected in parallel to two diodes. I'm going to call this guy D1 and this guy D2. My goal is to find the resistor value R1 if I want a current of 0.5 milliamps flowing through that resistor. And I am told that IS is equal to 0.1 femtoamps and VT is equal to 26 millivolts, meaning that this guy is operating at room temperature. So, anybody have any earthly idea how I might go about approaching this? How do I know how much current's going through the diodes? Okay. All right, so great. So you're Mr. McCallan, right? Yeah. So Mr. McCallan suggests that we could use Kirchhoff's current law to figure out how much current is flowing through our series connection of diodes. So he is suggesting that since we have 2 milliamps flowing into this node and 0.5 milliamp flowing out through the resistor, 1.5 milliamps must flow through that series combination of diodes. And I agree with that assessment wholeheartedly. So I'm going to say that ID, which is the diode current, it's the same for both of them, so I'm not going to bother with a subscript notation here, is equal to 1.5 milliamps. So now that we know the diode current, how does that help us in any way, shape, or form determine our resistor value? Right, now we can solve for the diode voltage VD, which would allow us to eventually solve for R1. So I want to be clear here, okay? Both of these diodes have a current of ID flowing through them. So both of them have a voltage drop of VD across them. So we should be able to find the relationship that twice VD divided by 0.5 milliamps is equal to our resistor value. Okay, so nothing particularly hard here. So let's go through the math and figure out what ID is. So we know that ID is equal to IS times EXP VD over VT minus 1. So we can divide both sides by IS and take the natural logarithm of both sides. Which gives us VD over VT minus 1. So from this, our diode voltage is VT times the natural log of ID over IS plus 1. So let's make sure I've done all my algebra here correctly. I might have screwed it up, it's always possible. So when I divide both sides by IS, I'm going to have ID over IS is equal to the exponential function. Take the natural log of both sides. So natural log there, natural log of the exponential just gives me the argument of the exponential function. I needed to add 1 and then multiply by VT. So everything seems pretty legit. All right, so I just know that I have a propensity to make dumb algebraic mistakes, so I like to go through and check it and make sure I didn't do that. So If we plug in our numbers here, get a calculator. So we would have 26 millivolts, 0.026 multiplied by the natural log of 1.5 times 10 to the minus 3 divided by 0.1 times 10 to the minus 15 plus 1. 0.815 volts. So R1 is twice VD divided by 0.5 milliamps. Multiply that answer by 2 and divide by 0.5 times 10 to the minus 3. And I get 3.259 kiloohms. All right. So that guy, fairly straightforward. I'm trying to decide if I want to do another example using this to show you how it can be difficult, or move on. I'm just going to move on. It'll be easier. We'll talk about the iterative method later when we need it. All right, so now I'm going to introduce the ideal diode model. All right. So the ideal diode model is this. Effectively, we treat our diode as a switch. Technically, it's a unidirectional switch or a one-way valve for current, okay? And so what I mean by that is if our diode is forward biased, the switch is closed, and if it's reverse biased, the switch is open. So instead of dealing with that nonlinear model, we can use this guy, which is going to simplify our circuit analysis, but it has some drawbacks to it as well. So our current voltage model for this guy, so here is current on this axis, voltage on this axis. With this model, there we go. Anytime our diode is reverse biased, we should see that no current flows. And when our diode becomes forward biased, we should observe that as much positive current that needs to flow can flow. So we have a pretty interesting input-output or current voltage relationship here, right? So reverse bias, VD is some negative value, and we know that the current is 0. And under forward bias conditions, VD is 0 and ID is some positive value of current. Okay. We can use this model to do circuit analysis. So let's look at another example real quick, where it might be obvious why we're going to avoid using the exponential model. Okay. Okay. So here's my new circuit. Let's call this guy diode 1. There's a resistor. A voltage source. Have another resistor. Here is another resistor. Short circuit. Call this guy diode 2. Voltage source. Diode 3. Resistor. Pull this over here so my old eyes can read the values that I have. 100 ohms, 1.5 volts, 10 volts, 150 ohms, 50 ohms, and 200 ohms. And our goal in this circuit is to determine the voltage drop over this 150 ohm resistor for whatever reason. Okay. So for the ideal diode model, application is fairly simple, meaning if we think the diode is on or forward bias, we replace it with a short circuit. And if we think the diode is off, we replace it with an open circuit, and then we solve. Now the problem is that it's not actually really easy to tell whether or not the diode is going to be forward biased or reverse biased. So we really just kind of have to make educated guesses or guesses, period, just to kind of figure things out. That's one of the big drawbacks of this model. So for instance, because there are 3 diodes, there are 7 possible configurations that we would have to deal with, which means we would have to analyze the circuit up to 7 times in order to get the one where we know all of them are behaving how they're supposed to behave. So let's don't think we're going to have to work it 7 times. In fact, I'm going to stop us from working it 7 times if we can't guess correctly sooner than that. But somebody tell me whether or not diode 1 is forward biased or on, or reverse biased or off. Just take a guess. So diode 1 is this guy up here. So you say forward biased. All right. Diode 2. Reverse. Diode 3. Forward. All right. So this is our first guess. So let's see what happens with that guess. So diode 1 you said was forward biased. So I replace that with a short. Here's 100 ohms. And if diode 1 you said is forward biased, then this is my current ID1. And we'll know that that guess, well, I don't want to say that explicitly. We'll talk about what's going to happen and how we're going to check things in a second. You said diode 2 was reverse bias, which means that's just an open circuit. So let's see, plus minus VD2. So diode 3 was forward biased. So this is a 200 ohm resistor. And our current, our diode current should be in this direction, ID3. 10 volt source. 150 ohm resistor, and here is V150. And it, actually, as it turns out, until we get our configuration correct, the voltage drop over the 150 ohm resistor is actually the least of our concerns, right? Okay, so our goal right now is to determine ID1, ID3, and VD2, okay? Because what we're going to do is we're going to check whatever values we get against our model and see if we broke it. And I'll explain what I mean by that shortly. So, how do you think, oh, and sorry, this was a 50 ohm resistor. How do you think we should go about solving for those quantities? Anybody care to venture a guess? Mesh, sure, why the hell not? It's a simple DC circuit. There's only 2 meshes, so that seems pretty dang easy. So let's give that a whirl. So I'm gonna label this guy as mesh current I1, and this guy as mesh current I2. Stop giving me that menu, that's not the one I want. So let's start KVL at mesh 1. So starting at the bottom left-hand corner, we're gonna have 100 I1 plus 1.5 volts plus 100 and, stop being weird pen, 150 I1 minus I2 is equal to 0. Anybody have any beef with my mesh equation there? 100 I1 plus 1.5 plus 150 I1 in this way, I2 in the opposite way equals 0. Seems legit to me, and I'm teaching the class, so I'm going to move along. KVL around mesh 2. We're going to have negative 10 plus 150 I2 minus I1 plus 50 plus 200, so 250 I2 is equal to 0. And let me make sure that that looks like a 5 and not a 3. So I have 2 equations, 2 unknowns. I can pretty easily solve for things, so let's do that real quick. Use our calculator here, system solver, 2x2 system. So let's see, our coefficient for I1 in our first equation is 100 plus 150 is 250. Coefficient for I2 is negative 150. Our constant value term is negative 1.5. For mesh 2, we have negative 150 I1. 250 plus 150 is 400 I2. And positive 10 volts. Let me move that over. Solve. And so I get 11.613 milliamps, and I2 is 29.354 milliamps. So what is ID1, the diode current one, with the direction indicated? Negative 11.613 milliamps. ID3 is going to be what? Same as I2, so 29.355 milliamps. And lastly, VD2 is going to be what? Yeah, so I2 times 50 ohms, right? So 1.468 volts. So are any of our assumptions regarding our diode being forward or reverse bias incorrect? Anybody have any idea? I would argue that 2 of them are. Okay. So ID1 is negative 11.613 milliamps. So that one's wrong because the diode current should be positive if it's forward biased. If we look back at our model, anytime our diode current is positive, we should be under forward bias conditions. Okay. So anytime our diode current is negative, would be under reverse bias conditions. So this guy was wrong. Diode 3 seems legit. Diode 2 is also wrong because we have a positive voltage drop over it, meaning that that should be a forward bias. So if this voltage is not 0 or negative, we made a wrong guess here as well, right? Because we assumed it was off and we have proven that the voltage drop across it is positive, which means it seems like it should have been on. So how do we want to change our parameters for guess 2? Intuitively, you would think, well, let's say this guy is off and now this guy is on, right? So let's give that a whirl and see what happens. So guess 2, diode 1 was forward bias and that was incorrect. So let's call it reverse bias. Diode 2 was reversed. Let's call that one forward. Diode 3 was forward and that one worked out okay. So that's what we're going to try now. Now, well, let's see what happens. I'm about to say something, but it'll be easier to just see what's what. All right, so diode 2. Let me look at this thing real quick. So diode 1 is reversed, so that's an open circuit. Alrighty, let's see here. Diode 2 is forward bias, so it's a short. Diode 3 is forward bias, so it's a short. So let me look up here real quick. Positive polarity on the right. Positive current down, positive current to the left. All right. So now we're trying to solve for VD1, ID2, and ID3 using whatever circuit analysis techniques, excuse me, we deem appropriate. So what do you want to solve for, and how do you want to solve for it? Okay, so mesh again because it seemed pretty easy. I don't have any problem with that because there are two meshes, but I would argue that it's actually unnecessary. So let me explain why I think it's unnecessary. Diode 2, we're treating as a short circuit. So it's shorting out that 50 ohm resistor. So really we just have one mesh because we know no current is going to flow through that 50 ohm resistor. So that's going to allow us to calculate ID2 and ID3. How are we going to go about calculating VD1? Well, if there's no current flowing through this 100 ohm resistor because it's connected in series to a short circuit, I would argue that once we know ID3, we could just do Kirchhoff's voltage law around the outside loop and call it a day. Right? Because we would know the current flowing through all the resistors, which gives us all known voltage drops except VD1. So mesh is too powerful if we think about it and realize that our diode 2 is effectively shorting out our 50 ohm resistor. So just to be clear, I'm going to do Kirchhoff's voltage law around that loop. We're going to use that to figure out what ID2 and ID3 are, and they should be the same exact thing because no current's going to flow through the 50 ohm resistor. And then I'm going to use Kirchhoff's voltage law around, well, that didn't work because I erased it somehow, this loop to figure out what VD1 is. Anybody have any problems with the methodology I'm choosing to use here? Anybody see anything wrong? Okay. All right, so our first loop in dark blue, we're going to have -10 plus, let's see, 150 plus 200 is 350 ID, and I'm going to call it 2, 3 because it's both is equal to 0, right? So I'm saying I have -10 volts and the voltage drop over this 150 ohm resistor, which is going to be 150 times ID3 plus the voltage drop over this guy, which is going to be 200 ID3. And because none of the current ID3 branches off or is able to branch through this, ID3 has to be exactly equal to ID2. So this tells me that ID2 is equal to ID3 is equal to 10 over 350. .572, I don't know, 571, I rounded poorly, milliamps. So both of those guesses seem okay, right? They're both positive values for current, so that seems legit. If we do Kirchhoff's voltage law around the light blue loop, we have -10 minus VD1 plus 100 times 0 because there's no current flowing through the 100 ohm resistor since it's connected to an open circuit. So I'm not going to write that down. Plus 1.5 volts plus 200 ID3 is equal to 0. And I'm going to be just oodles of lazy here and let my calculator solve this for me. I'm just going to use the numerical solver. Let's see, -10 minus x plus 1.5 plus 200 times 28.571 times 10 to the minus 3 is equal to 0. Solve. And I get VD1 is negative 2.786 volts. So what does that mean about my guess for the state of diode 1? It's also correct. So this is our, this is the correct representation of the circuit, and now we would calculate that voltage. Let's see, I think it was B150 with this polarity pretty easily. Let me make sure, yeah. So 28.571 times 10 to the minus 3 times 150, 4.286 volts. Okay. So there were 5 other possible combinations that we could have gone through, but we got there pretty quickly. The thing that I want to warn you about is that in our first iteration of this process, we found out that these two were wrong, and so we changed our decisions. It is complete happenstance that that worked out to be the right combination. Okay, that is not a guarantee by any stretch of the imagination, because every time you change these things on and off, you're analyzing an entirely different circuit. So that fundamentally changes the relationships you have. So we had a happy accident here that we only had to work the problem twice, but we could have had to work it significantly more. All right. Now, if we went back and revisited our first problem and used the ideal diode model, we would have a bit of a problem, right? If we treat both of these guys as just simply short circuits, then there is no resistor value that will cause a current of 0.5 milliamps to flow through it, because we would say that all of the current should be flowing through the shorts that are represented by our diodes. So this problem works out nice and well with the exponential model, but the ideal model falls apart. The other problem would just be a massive, massive pain to work using the exponential model. So we're using the ideal model and we're getting a reasonable approximation. There is a happy medium, okay? So if we look at this characteristic curve for the ideal model, what's wrong with it? Anybody have any idea? So what if I were to draw a picture of the characteristic curve for the Shockley model? Might make things a little bit easier to see. Here's V, here's I. So we should have something like this. Let me increase the line width here. Draw, you stupid pen. There we go. Should look something like that, where this bit is much more flat, but I can't draw it. So down here, we're representing our reverse bias breakdown, but over here, we see that the diode doesn't exactly turn on at VD is equal to 0 volts, right? It takes some time because of this exponential relationship for the diode to actually start conducting significant amount of currents. So our next model is what's called the constant voltage drop model. And it is a happy medium. between the two. All right, so we take our regular plain Jane diode, and instead of approximating it as a switch, we are now going to approximate it as a battery connected to a switch. And the battery here is just representing the shift from 0 volts to get our positive current conduction to occur at a voltage that's greater than 0. So for forward bias, we would literally just treat this as a battery, having a value of VD on, and we expect our diode current ID to be positive. And for reverse bias, we still have an open circuit. We expect VD to be negative. On, O-N, because we're saying it's conductive. Our current voltage, sorry, what was that? Yeah, still have to guess, but your answers will be much more accurate than they were with just the ideal model. So yeah, the guessing is still going to happen, and technically we're going to see, you know, I'm probably going to run out of time before we get into that for, I guess, next Monday's class. We have to guess with the exponential model too. So the circuit that we had settled to a unique value very quickly. But if we were to try to use the exponential model in circuits with voltage sources and stuff like that, we're going to see that it's also an iterative process. So unfortunately, we're never going to get to just use handy dandy relationships or anything like that. And it's because these diodes are non-ideal or non-linear, excuse me. So we're gonna see that, and this is a happy medium for some quick back of the envelope calculations on trying to figure out how these things behave in a circuit. It's going to be, so if we think of a diode as a switch, which is either open or closed in a DC circuit, that's kind of pointless, right? So what I mean by that is, before we analyze this guy, so we know that this diode here was supposed to be, or we found it to be reverse bias. So my question to you is, why would we put it in the circuit at all if it's not conducting current? There isn't a good reason, right? Diodes aren't used a whole heck of a lot in DC circuits. They're used an awful lot in AC circuits to make current only flow in one direction. So as a quick aside before we get into this, I'll do this way down here on an entirely different page so that we won't run into it. Let's say that I had a simple circuit like this. we want to find VR of t using the ideal diode model. And Vs of t is simply, let's say, 5 volts times cosine of 2 pi t. So if we plotted this guy, our Vs waveform would look something like this, right? Simple sinusoid, nothing fancy there. What is our, using the ideal diode model, what's going to happen? Well, when Vs is positive, this is a short circuit, and so we should see, let me do it in orange, that we get something like this. So for the positive half cycles, the output voltage matches the input voltage perfectly. But for the negative half cycle, what happens? This is an open circuit, which means the voltage drop over the resistor is 0. This is a rectifier circuit, okay? And it's called a half wave rectifier. It's rejecting all of the negative half cycles. Now, if I did something wild here, and I put a capacitor in parallel with this resistor, we would see something similar, except that now the capacitor has stored energy, and if we size our capacitor correctly, we get something like this. This rectifier circuit is how effectively like battery chargers and things like that work, okay? So the voltage that comes out of that wall outlet, what is it? 120 volts RMS, which means it's a sinusoidal voltage having a value of 120 square root of 2 times cosine 120 pi t plus whatever phase angle we happen to start looking at, right? Sinusoidally varies, goes through 60 cycles a second. Our phones have, I think, a 3.3 volt battery, at least mine does. Most Samsung Galaxies and all that kind of stuff are too. Battery is an AC circuit or a DC circuit. It's DC. So if we applied a sinusoidal source to try to charge a battery, what happens when the battery, or excuse me, when the sinusoid goes negative? The battery starts supplying the sinusoidal source. This is the type of circuit that's used to make sure that the charging current only flows in one direction. And we can size our capacitor here to make the decay as small as possible so that it's really just going to look like a very, very close to a DC signal with a little bit of a ripple. Okay. That's the electronics we're going to be getting into probably, well, definitely next week, talking about half-wave rectifiers, full-wave rectifiers, and all that kind of jazz. But I just wanted to give you kind of a heads up on where this stuff is going and where these models can be appropriate. If we applied our constant voltage drop model, this is what it would look like. So the size of the peak is slightly smaller because we always have that 0.7 volt or whatever offset drop associated with it. And then with the capacitor, we'd have something like this. So it's a little bit closer to real. All right. So coming all the way back around. Here's our diode current. Here's our diode voltage for the constant voltage diode model. Our IV characteristic curve should look something like this. Medium thin. So it conducts no current until we turn it on, and then it conducts as much current as it needs to conduct. We could go through and rework this example problem using the constant voltage diode model with the assumptions that we made in our second guess here. So diode 1 is off, or diode 1 is reverse bias, and diode 2 and diode 3 are forward bias. And we would see that we get a different number here, which makes perfect sense, right? So if we put a 0.7 volt source here, replacing this guy, then the current flowing through this guy is going to be pretty easy. It's just 0.7 volts divided by 50 ohms. You know, we could do KCL. It's going to be fairly trivial to analyze, but we'll see we'll get a different number. Now let's look at cycle all the way back here. What if we use the constant voltage drop model here? Do we have that weird thing where there is no resistor value that works anymore? No, right? So if we assume that VB on was 0.7 volts, which is a very common voltage for a silicon PN junction or silicon diode, what would the resistor R1 be? 1.4 volts divided by 0.5 milliamps. $2,800. So we originally got 3.259 kiloohms. Using the constant voltage drop model, we get 2.8 kiloohms. So it's not exact by any stretch of the imagination, but it's a much closer approximation than we would get just using the ideal model. All right, so let's look at step out of the way. How we can find the IV characteristics of simple circuits using the constant voltage model. So circuit A, or circuit number 1. We have voltage Vn that can range from negative infinity to positive infinity. Connected to a diode, connected to a resistor. So this is our half-wave rectifier thing again. All right. Let's do this. So how's this circuit going to behave? So what's the current going to be when Vn is less than 0? Let's start there. 0, right? Definitely, the diode is definitely reverse bias when Vn is less than 0. So we should see that the current is 0. And actually, let me put something in here real quick, just for the sake of argument. That just says VD on. All right. What is the current going to look like when Vn is positive but less than VD on? Pardon? So if Vn is less than VD on, so let's say that this were 0.7 and this guy were 0.5, we'd still look effectively like we were reverse biased. So it's still going to be off. So effectively, until our input voltage exceeds VD on, this guy is off. What happens after when Vn is greater? It's on. Is the current going to go like what's a? All right, so let me explain. Yeah, it's going to be a linearly increasing current, right? Something like this, where this slope is 1 over R. Anybody have any questions about why it increases linearly like that? So are using that constant voltage drop model, this guy becomes a battery in series with a short circuit. So V divided by R is just going to be some value. So as V increases, current should increase linearly. All right. So let's try something else. Vn take that back. I don't want it to look like it's just the current flowing through the diode. So same type of analysis. All right. So what's going to happen in this guy when Vn is negative? Is this guy going to be forward biased or reverse biased? Or diode forward biased or reverse biased? Reverse biased. So that's going to look like an open circuit. So when Vn is negative, all the current I is going to flow through this resistor R. So we should have a linearly increasing current. And it's going to continue to linearly increase until Vn reaches VD on. What happens when this guy becomes forward biased? It's a short circuit. So all of the current, so we have an input voltage divided by effectively zero resistance, because we know that all of this current will bypass the resistor. Should get something like this. What we're developing here are load lines for simple circuits, so we can see how they're going to behave based on what simple input voltages are. This is yet another method of analyzing diode-based circuits. Let's see. Circuit number 3. All right. Let's make this the last one. All right. And let's call this guy R1 and R2 to make things easier. Oh, sorry. This slope is 1 over R. All right. So when our voltage Vn is negative, this guy going to be reverse biased or forward biased? Okay. So you're saying when Vn is negative, it's going to be reverse biased, or excuse me, forward biased. And to me that makes sense because ground here is at a higher potential. So this guy should look like a short circuit. Okay, I'm okay with that. So it's going to switch when we get to negative VD. Actually, let me put it up here on the other side. Right? So when Vn gets larger than negative VD on, that's when it's going to switch into forward bias, or reverse bias. Does that make sense? So let's think it through here again. So Vn is some negative number, which is at a lower potential than ground. Because our anode is on the ground side and our cathode is on the Vn side, that means that this is at a higher potential than this, which means this is acting like effectively a short circuit in series with that 0.7 voltage source, where we have a positive polarity terminal on the right-hand side and the negative polarity terminal on the left-hand side. When Vn gets above this, so more positive than this particular value, this guy goes into reverse bias, and our input sees both of those resistors in series. So it's going to look something like this then. Oh, it should cross through 0. So this slope is 1 over R2, and this slope is 1 over R1 plus R2, something like that. All right, so I think something like this would be a great conceptual style question to ask on the exam. So just give you a heads up, expect something like that. We'll be working on it over this weekend. I think this helps reinforce the current voltage relationship between, for the constant voltage drop model. Let me think. All right, we got 7 minutes, so let's look at the WebWorks again real quick. Probably not logged in. So problem 1, reverse bias PN junction. Like I said, we've covered all that. We should be good to go there. Problem 2 is exactly what I worked in class earlier today, except the numbers are different. So that guy should be real easy for you guys now if you didn't figure out how to do it before. Like I said, we already had enough information to do it, but it might be a little tedious. I told you exactly what to do. This guy right here is very similar to what we were just doing, but in my opinion, it's actually much easier. So let me explain excuse me, what I mean by that. What is this? Yeah, okay. So we're told explicitly that VD on equals 0.7 volts. Whenever you're told that, that means you should be using the constant voltage drop model. For each diode in the figure above, for each circuit, determine the change in V out as V in is changed from 2.7 volts to 2.9 volts. So if we look at how these things are drawn, V in is being changed from 2.7 to 2.9. So V in is always positive. So is this diode forward biased or reverse biased? Forward biased, okay. Is this diode forward or reversed? Forward. What about this guy? What about this guy? What about this guy? What about this guy? Also forward. So all of these are real trivial. You don't even have to think about it too much. All right. So let's see here. So if we treat this guy as a 0.7 volt drop in series with a short circuit because it's a forward bias resistance, when 2.7 at the end changes to 2.9, our output should change to from 2 to 2.2, right? Because if our output voltage changes by 0.2 volts, excuse me, our input voltage changes by 0.2 volts, our output voltage should change by 0.2 volts as well. Real trivial, all right? What's going on with this guy here? Now we got 2 diodes. Does that make this any harder? We have a 0.7 volt drop here and a 0.7 volt drop here. We have no idea what the voltage drop over the resistor is. We have no idea what the amount of current flowing through anything is. But I would argue that the output of this guy is the exact same thing as the output of this guy. The current's going to go down, but the output voltage is going to be exactly the same, right? So we're going to have some unknown, so if we did Kirchhoff's voltage law, we would have negative Vin plus Vd on plus V out is equal to 0, which means out is equal to N minus Vd1 again, or Vd on again. So it's going to be from 2.0 to 2.2 volts. Now let's look at this guy over here. Our output voltage is the drop over the diode. We're using the constant voltage drop diode model. Does changing the input voltage change the voltage drop over the diode? No. So V out is 0.7 and 0.7. Exact same thing here. We're picking the voltage drop over the diode itself. With a constant voltage diode model, this means it's 0.7, regardless of what we have here, as long as it's forward biased. So this problem is an absolute joke to solve using the constant voltage model. Yes? So, using the constant voltage diode model, we are replacing all of these guys with a voltage source in series with a short circuit. The voltage source has a value of 0.7 volts. So if I change the input voltage here, what that's going to do is it's going to change the current that's flowing through my resistor, but it's not going to affect the output voltage because that's just the drop over the diode, which has a constant voltage. And the exact same thing occurs on the other circuit. And then problem 4, I believe I said last time that you guys should have been able to work that. Let's look at it real quick. Yeah, this is a joke at this point. All right. So Ronnie, could you hand this around and try to? All right. So on Monday, when we get back, we are going to talk more about, I guess, really practical applications of diode circuits. So we're probably going to get more in depth into half wave rectifiers, full wave rectifiers, voltage regulators, all that kind of jazz. Things that you can use diodes in now that we have enough background to analyze their circuits. All righty. Hope you guys have a great rest of your weekend.